Thanks a lot, guys. Okay, we'll kick off the second morning session. So it's my distinct pleasure to introduce Professor Steve Coombes to you. Steve is a theoretical physicist and mathematician by training and by practice, but also working in, I guess you would say, applied mathematics. Do you identify as an applied mathematician?
Definitely, it's my comfort zone.
Right, okay. And I sort of indicated earlier, and I was pleased when Steve was going through his slides, that he has evidence of this is one of the things that Steve has to his name, which I think is a real contribution to people like me at the time, as he wrote the book on neural fields, so to speak, which, as I mentioned earlier, is one of the underlying kind of principal topics of this meeting. We already heard from Dimitris about this. I mean, wrote the book is a stretch because I guess it was an edited volume, so
yeah, I can't claim
tell me off for that. But there's quite a lot of content in it from you, and more importantly, built the book that really introduced a lot of the mathematical techniques of neural fields to an interested neuroscience audience, and has been continuing to push the new directions in, I mean, both neural fields proper and other areas of mathematical neuroscience. I think we'll hear about both of those today, and a leader in the field. So my pleasure to introduce Steve Coombes.
Okay, thank you, John. And thanks to all the organisers for inviting me to be here. It's a real treat, so thank you. Yeah, I'm an applied mathematician. I work in the Centre for Math, Medicine and Biology in Nottingham, and I'm going to tell you about some things I've been working on. Okay, so it's going to be sort of an overview talk, not an in-depth talk. John already did this. He sort of said, "Well, I better tell you what modes are." I've not met John before. We haven't had a chat about modes, so this is my take on modes. Okay, so you can see where I'm coming from. So modes for me. I'm a maths person, you know, so there's a system of ODEs, you know, very simple sort of toy model of a neural network sitting there with some connection weights and W's. As a network model, John mentioned neural fields. If you stretch them out in space, you might consider things like spatial convolutions, okay? If you linearize these models, choose the non-linear function f to be, you know, just the identity. You can talk about exciting certain patterns of activity, which would be the eigenmodes of the structural connectivity, the W's, okay? So for me, modes are eigen things, okay? Just what John said. But what am I linearizing around? So that'll come up again later in my talk. So if I think about a neural field in the plane, and I've got a convolution operator in space, then the eigenmodes of that are just nice doubly periodic patterns, and you can get neural fields to excite these patterns. But maybe you might think they're a little bit, boring. But if you can excite patterns of different, incommensurate spatial frequencies, then you can get cool patterns. So this is literally just a bit of eye candy. This is a neural field, something in the plane that's a mimic of neural activity, and I can make a lovely quasi pattern. But there are some modes hidden here. And one of the first papers I read on sort of neural pattern formation and modes was due to Axel. So if you've not read this, I think it's a really nice starting point for studying neural fields. And if you're curious, this neural field here that makes this lovely quasi pattern, a bit like the quasi pattern on the back wall if you turn your heads around, all you need is a model of neural field with short range excitation, long range inhibition, and you put some squiggles, you put a little bit, some oscillations in the tail of an interaction or the midsection of the interaction. Okay. This talk, I want to focus on the role of delays in exciting certain modes. So it can be very, very useful to extend these models of things on networks to include the communication delays between the nodes. So you might be given some sort of structural information, some connectome data. You think, well, I can pull out some modes of that, eigenvectors of this structure. But you might want to explain some data, some functional connectivity data, which isn't built out of the modes in the natural ordering, then they come out from the ordering of the structural system. And delays are a really, really nice way of exciting modes in novel orderings. Okay, so I just want to say delays for me are fun things to put in dynamics. They make models rich and interesting, and it's highly relevant to neuroscience. So I'm definitely not the first person to realize the importance of delays in neuroscience. And I've got this, I'm not sure if it's a quote or a paraphrase about saying delays are important. And even if I put up silly pictures like this, implying that functional connectivity patterns aren't dynamic, they clearly are very, very dynamic. Okay, so delays are very important for exciting certain patterns and making things move around in time. Okay, so that's modes for me. But now I'm going to, I've got three things I want to sort of cover in this talk. Rather than going for some sort of universal picture, I'm going to ask questions like, does it matter how you build these models? Does it matter what dynamics I put on a node? I mean, we've probably all heard of the Wilson-Cowan models or Janssen-Ritt models or Robinson models or, mathematical models of oscillations at Stuart Landau. So should I start with those models of the oscillations and put them in the network and study them? What model of the synapse should I choose? How much biology should I put in? If I'm talking about general anesthetics, for example, like Axel did, should I worry about those details? What am I really blocking? And, when I think about connectome data, and I've got a very, very large network with, things interacting with delays, where's my sort of toolkit for analyzing networks with delays? How much mathematics is already out there to understand that, and how much do I, have to pragmatically develop? What choices of coupling should I make? Is it going to be difference coupling, Laplacian coupling? Is it going to be full-on non-linear synaptic coupling? Where do I stop? And for me, where I stop is, I want to be able to do some analysis in the future. So I want some relatively tractable models. Okay. So let me start with the first question, the mass choice. Okay. So I work at Nottingham, and my colleague there, Matt Brooks, is developing these OPM MEG technologies. He came to see me and said, Steve, I've got this data. I know you do modeling, build a model. And the challenge is this. So he's, looking at power spectra. I'm recording from motor cortex in response to movement. You make a movement, power in the beta band drops away. You stop the movement, power in the beta band comes back in anger. Okay. And the notion is that, where the power drops away, it's really because the recording technology is seeing some desynchronization of the tissue. The tissue underneath the recording sensor isn't giving out enough coherency to be measurable. But here, when we've got the overshoot in the power, that's a signature of over-synchronization. So we've got event-related desynchronization, event-related synchronization. Okay. He was at the time working with a psychiatrist colleague, Peter Lidu, who's very interested in this as a potential biomarker for schizophrenia because the rebound was diminished in patients. So, I mean, the challenge is to build a model for Matt, and then the bonus is that Peter gets a model that he can use in sort of computational psychiatry setting. I'm only going to talk about this bit, okay? So I really had a hard time picking a model like Wilson-Cowan or something, because if you ask a Wilson-Cowan model, at the population level, how synchronized are you? It doesn't give you an answer because it's not seeing individual neurons. It can't tell you how coherent they are or not. So we just went back to the drawing board. Unfortunately, the drawing board wasn't empty. There were many people beginning to work in this space. But what I mean is I want to build a little patch of, I want to build a model for a patch of cortex, but I want to start with some underlying microscopic model, because if I've got a microscopic model that spikes, I can say, well, how coherent is the pattern of spikes? And can I change that pattern? So things like Hodgkin-Huxley models, conductance-based models, they're too hard to work with for me. So I've gone to a very, very simple single variable model. The V for voltage, I tells me which node I am in the network, and it's going to be a quadratic integrated fire model. So I don't have any gating variables. I just have something that says if this voltage ever gets big enough, you make a spike, you reset, and off you go again. And we'll have some conductances in the network that are driven by spike time. So these T's, this is the, J tells you which node you're on the network, M tells you, it's the M spike of that node. But the idea is the following. you can simulate this system, you can plot little red dots where the neurons spike, and you can see patterns of here quite synchronous behavior. And the idea would be if you put some sort of stimulus into this network, the raster plot would change such that, you might create less synchrony, and then when you remove the stimulus, the system over-synchronizes, and that can explain the data as seen in Matt's OPM MEG experiments, okay? And here there's some degree of heterogeneity. There's a background drive here, which means all the neurons, synthetic neurons, can fire at slightly different frequencies. So this is the distribution of background drives. It's just drawn from a bell-shaped curve, but there's a center eta naught and some sort of spread gamma. That's it, very simple model. You have to choose a synapse model. George Green used to be the miller in Nottingham. He's also famous for Green's functions and Green's theorems. So I'm going to adopt a model of the synapse, which says, you receive a spike at some time and you measure postsynaptically, and the response takes the time to peak and it drops away. It's just a typical shape. Grows linearly in time, drops exponentially zero at later times, but that function called eta is going to be the Green's function of this second order differential operator called Q. Okay, so my model of the synapse is I get a kick, my response goes up and down, and I can control the time scale of that with the parameter alpha. 1 upon alpha is the time to peak. I'm going to switch language from voltages to angles, because my single neuron model is just one-dimensional. So I can say, where am I on my cycle? So I'm going to pick an angle. I pick this half-angle transform. Doesn't matter too much what I pick, but the idea is this. So the quadratic integrated phi model, just voltages swing up on the constant drive. You get reset, you swing up, and you see the blue dot. I'm just mapping out to the circle. I'm choosing some sort of dynamics. It's got non-uniform rotation, but it's just maybe easier to visualize angles than voltages, but it doesn't matter. You go back and forth. And what I want to do is build a mean field model, okay? So rather than pick, your favorite neural mass model off the shelf, let's derive one and see if it can explain Matt's MEG data. So there's many, many routes to mean field. But what I'm going to do is consider the very large limit. So thermodynamic limit, infinite number of neurons. And I'm going to be interested in what is the distribution of the voltages or the distribution of the angles in this network. And the network is globally coupled. There's no structure yet, okay? This synapse is a bit of heterogeneity, but global coupling. And there was this very nice paper by Luke Barreto and So in 2013 that says, well, if you're looking in the angular framework, I just want to look at the distribution of angles in this system. Well, hang on, angles live on the circle. This distribution must therefore be periodic. So why don't we write a Fourier series and try and work out all the Fourier coefficients? So that's what they did. They just said, if I factor out the distribution of drives, the distribution of angles, must be some sort of Fourier series. So usually in the Fourier series, you give yourself a lot of work. There's an infinite set of coefficients you'd have to work out, okay? But what they said is, for this model and this model only, this QAF model, all these coefficients are powers of some single number. So if you can think about it in terms of notation, it used to be an A subscript n, where n would index where you are on the series, and now this is just a power. Okay, so this is a Fourier series of one amplitude. Okay? And what they showed is, if you substitute this into your continuity equation, you've got conservation of oscillators, you can show that this works. It's called the Ott-Anderson ansatz, as long as you pick A to have a certain dynamics. And the nice thing about A, they also showed it has a physical interpretation as the Kuramoto order parameter, or its conjugate. Okay? So what do I mean by Kuramoto order parameter? Probably most of you are familiar, but all the angles, these are all the little individual neurons doing their own thing. The order parameter is just what their center of mass does, the big black arrow, that's it. Okay? So it's interesting that the physical interpretation of this coefficient is the order parameter. And the dynamics, therefore, is in terms of solely of the order parameter, which has a physical interpretation as something to do with synchrony. So if that black, here you can see it's quite synchronized. The center of mass is quite out towards the edge of the circle because all the neurons are out there, okay? If they're all equally distributed around the circle, the center of mass would be, pulled in all directions, the center of mass would be right in the middle, no synchrony, okay? So we guess the distribution of angles. Asynchrony would be a flat distribution, synchronous would be a delta function, and then some mid-range synchrony would be just a bump. This is an exact solution. It's really, really, luck. Okay. I don't know how Ott and Anderson came up with this, but it does work. Okay, so what we do, we go from so imagine we have a population of quadratic integrating fine neurons here. As long as they're globally coupled and there are enough of them, then I know there's a mean field model. But the mean field model is given in terms of the dynamics of this Fourier coefficient, which is the synchrony parameter. Okay, the synchrony evolves according to this second order, Riccati equation Z. Doesn't matter too much what it is; it exists. Okay, so many neural mass models are written in this form. You have some sort of conductance, you have some rule for evolving them. That's my second order differential operator. And you have a source term, which is typically a sigmoidal firing rate. Okay, you make up the choice. It's a sigmoid. Now you get exactly the same structure. The spike trains get washed away. There's a rate sitting here, but the rate turns out to be a real valued function of the Kuromoto order parameter, which is dynamic. So you need four. If I want to describe this population, I just need four equations: two to tell me how synchronous I am, because this is a complex number, and two to tell me how the synapse is evolving, because I chose a second order synapse. So Wilson-Cowan, if you like, is two equations. This is four. So if you're doing computation, it's not really a big burden, but you get a link back to microscopic behavior. So you can either simulate all the little circles or the four equations that give you the mean field dynamics. Okay? So I'd vote for four. Does it explain rebound, or is it consistent with rebound? Well, I'm doing plots here in the sort of synchrony plane, the Kuromoto order plane. Let me show the second picture. So the idea is you set up one of these population models at beta, and then you interrupt it with a signal, and I just picked a simple signal on-off. So I drive it and I switch it off. The frequency here goes away, as it does in the real phenomena. It might come back in anger and gamma or somewhere. You switch it off and you get a rebound phenomena and decay to rest. But you can now sort of begin to explain or understand this geometrically. There's one frequency, the beta, and then I kick it, gets pushed to a higher frequency here. And when the signal is released, you get the green curve, you go back to your base oscillation, but you go the long way around, you head around near the edge of the disk. But in the edge of the disk in Kuromoto space, whatever this thing is called, that's where synchrony is high. So you can say, I'll get rebound because I have to take this path. Okay? So if you've got other phenomena you want to explain, or much longer timescales, you can think geometrically now, put other phase space structures in here, saddles and things, make the phase space really sticky to slow dynamics down even more. This rebound is taking about half a second. In reality, it can go from half a second to 10 seconds. So it just gives you some mechanistic ideas about where rebound comes from. There's, what time did I start? 15, right. So that was one route to the mean field model. And some of you might have worked in this field know there's another equivalent route, which basically says, let's guess the distribution of voltages, in the QAF framework. And you guess a Lorentzian or Cauchy distribution with a center Y and a spread X. I'm not going to go for this. I'll just give you the highlights. But basically, again, if you make this guess, it works. And the physical interpretation of this center is it's the average voltage in the system. And this spread here is the population rate in the system. Okay? But there's a very, very nice link between the two. Basically, because in the voltage framework, you can relate it to, I had this half-angle transform, but technically it's a Mobius transform of e to the I theta. But in one framework, you've got a variable that says Z is really important, synchrony. And in the other framework, it says rates and voltages are really important, but they're equivalent. And the equivalence is the following. It's really via this Mobius transformation that such that if you make a complex number, which is this, you take the rate and add it to I times the average voltage, you can get a map between synchrony and this new variable. Okay, so if you like doing mega experiments where synchrony is sort of sitting in your thought patterns, maybe this is really cool. But if you're doing voltage-sensitive dye experiments, you might like this framework because you can see voltages directly. Okay, so this is I think it's just a nice model that's a little bit alternative to choosing Wilson-Cowan, and it's only a couple more ODEs. It's not a big deal. Okay. Some other applications. So I mentioned beta rebound, but I was really talking about trial average phenomena. In realizations, these patterns of activity come in bursts, tens, hundreds of milliseconds. So we, motivated by some further experiments of Matt, we just add a little bit of noise to the model and we could explain this data extremely well. So in the spirit of, Axel's approach. Can we get realistic patterns of functional connectivity out by putting these, we built them for one reason, then we put them in a network, can we play games and get, predictions for functional connectivity patterns? Other people have put these models in the virtual brain environment and looked at resting state dynamics. So it's a model that, I'm not giving it to you fresh. Other people are already using it. I'm just trying to advocate for more people using it. And of course, I completely sidestepped, how do you fit this to real data? Maybe John will pick up a discussion in that space for us. But, okay, I'm just saying it's a nice candidate model. It's not too computationally burdensome. Why don't we continue to explore it? I like patterns and neural fields, and so it's very easy once you've got a point model to stretch it out in space. So there's no problem building a neural field. Luckily, this reduction, this Ott-Anderson reduction, which is exact, doesn't. There's no penalty for including other forms of communication like electrical connections between cells as well. So you can put even more biology in the system. And then at the field level, you can choose patterns of connectivity. You can include delays and so on and so forth. And you can just get really, really pleasing planar models of what these tissues will do. Okay, so I'm not saying this is a candidate for what's going on in the brain. I'm just saying it's a really, really rich pattern-forming system. This is a planar neural field, and I'm tracking a synchrony order parameter, which Wilson-Cowan could not. And you get cool patterns of rotation organized around cores. Okay, so there'll be some references here and there. Okay. Just again to reinforce that this model is very, very rich. Go back to the sort of traditional architecture that you would see in the Wilson-Cowan model, E and I in 4 populations of synapses. You can write these models out in the synchrony representation or the rate and voltage representation. It will look unfamiliar model. I can include the gap junction. So every time you see something called kappa V, V for voltage, kappa is just the strength of gap junction coupling. But then you can pick your favorite, because I've got gap junction coupling, it might be unphysiological. I'm putting gap junctions between excitatory cells, this is notation, and between inhibitory cells. But you can walk around in these parameter spaces and just see interesting bifurcations that aren't there in the standard neural mass models. So this thing here is basically, this color coding is just showing if I've got a time series, how many sort of spikes do I get in a typical envelope. So you might get things, you might get a chaotic attractor, or it's very easy to generate torus bifurcations in this system. You can walk around in this parameter space and go from one sort of rhythm to another. I've put these labels on tonic and clonic to suggest we're thinking about this in the epilepsy context, especially as the strength of gap junctions is known to change during seizure states. But this, just a bit, it's a rich model, that's all I want to say. Okay, you can stretch the model out into the plane, you can have fun stretching out onto folded surfaces, and then you get to play games about the model's got some microscopic dynamics in it, gap junctions which aren't in standard neural mass models. What are the consequences of the global dynamics? So here again, just a gratuitous simulation. I'm changing the level of gap junction coupling in this simulation as compared to this simulation to show me that I get a lot of global control over a local tuning of a parameter. Okay, the color code here is just how hub connected that bit of the tissue is, but it's just a bit of visualization. Okay, the challenge I want to get to next, that was a node, how to choose a mass model. Here's a candidate. How to choose a synapse? Well, I just took the one everyone loves anyway. I didn't muck about in that space. But how do I do delays in these models? So even delays in standard neural mass models are really very challenging to address. So this is like a standard Wilson-Cowan model. U and V stand for excitation inhibition. I is just a node in a network. There's a sigmoid sitting here. I've got some intrinsic delays, tau naughts, and I've got a set of delays between nodes I and J. So every time there's a connection between nodes I and J, I allow a delay between them. And you say, well, what's this thing going to do? Well, I can simulate, which is great and important. But what analysis can I do? Okay. So one way to do analysis is to, change the model. Okay, if it was Wilson-Cowan, that was a sigmoid. If I turn that into an on-off situation, you're either firing or you're not, that means my dynamics is decay +1 or plus 0. Okay, it's a piecewise constant system. You can study it with UK A-level mathematics. So I just steepen up the sigmoid and I can make lots of progress. And so I might be able to find, periodic orbits in this system. And then I can talk about neurons or nodes that share a common orbit, like a synchronous solution, and do lots and lots of analysis. So this is a simulation of the system with the Heaviside non-linearity. Other people might say, well, I'm never going to do an experiment where that's going to be a close approximation. I won't do that reduction. But a lot of these nodes and these networks, they just oscillate. And there's been a theory of phase oscillators around for a very, very long time. So I might reduce this system down to something. If I've got a limit cycle in the plane, and I live on the limit cycle, I just need to know one number to tell you where I am, which is the phase on that cycle. Okay? So you might imagine writing down some sort of transformation to an angle-only description. I've got some sort of rotation rate that I can work out. I've got some coupling, and I've got an effective interaction which I can derive. And now I keep the delays by just saying, well, if I'm experiencing the activity of node J, I still have to look back in time. That's it. So, and there's standard systematic ways of deriving these H's from your choice of model, which is nice. But they only work if the coupling is weak. Okay, so if you don't have weak coupling, you wouldn't do this either. Okay, and then the next approach is to really, well, just solve it. It's non-linear. I don't care. I'll just solve it. Okay, it's impossible in general. So what I'm advocating for here is a hybrid numerical approach. If I'm only interested in oscillations, and they're periodic, maybe I'll just go for some sort of Fourier description and again calculate Fourier coefficients. So this is a simulation where this, I'm not doing Heavisides, things are smooth. I can see some lovely periodic orbits in whatever plane I'm plotting. These little dots represent the activity of 30 nodes in a network. Okay. Okay. So this is sort of the mathematical bit. So I'll go quite quick. But the idea is if you've got an oscillation, it's not unique to this story of neurons. If you've got an oscillation that might arise in a very, very simple scalar delay differential equation, there's a single delay here. If you assume a Fourier series solution, then your job is to compute all the Fourier coefficients. That's all you need to do. Okay? And you hope that by truncating that sum, you can get away with a lower dimensional description. But if you sample the periodic orbit at a finite set of times, let's call them these sampling times Tn, you can relate the samples of your state to the coefficients of your state as long as you do enough sampling. So if I collect all these samples in a big vector called x, and I collect all the amplitudes that I need to work out in a big vector called a, there's a linear relationship between them. And this S is just a very simple matrix I can't see on here, but it's just a van der Waals matrix. There it is. Okay. So by doing this, you can turn your differential equation problem into an algebraic problem. I just substitute this guess into my system of differential equations, and I've got a big set of unknowns for these real coefficients of the samples. Then if I can solve this using fsolve in MATLAB or your equivalent, then I can work out all the Fourier coefficients by just inverting this operation. So it's just a practical numerical tool, but it also opens the way or the door to do Floquet theory or stability theory, because on the first slide I said this is a mode, I'm linearizing around maybe a steady state, but now I want to linearize around something that isn't a steady state. So it's what are my eigenmodes? Okay, it's a different framework. Linear stability here says take your orbit, add a periodic function and something scaled out in time of e to lambda t. And if lambda is positive, or the real part is positive, then it gives you a route to doing bifurcation theory, because that would be an unstable solution. So I'm going to just flag up a lovely determinant here. Looks lovely to me. But basically, I can pin down the spectral problem for this in this harmonic balance approach by saying I need to compute things like Jacobians, exponentials that depend upon the delay. But basically, this is just I can write down the spectrum as the zeros of some complex function. This is a Wilson-Cowan node in its own. Blue is just a periodic orbit. I compute it with harmonic balance. And the spectral theory allows me to basically look at the zeros of this function, and I write that as I write the real bit and the imaginary bit and plot the intersection of the two. But basically, there's a red curve and a blue curve, and if they intersect, that's an eigenvalue. So I can see there's loads of zeros, I expect, because I've got time translation invariance, but I can determine the stability of periodic orbits. Okay, that's one node. Okay, what if I build a large-scale brain network with many nodes? The ideas go across, at least for certain classes or types of solution. So let me just briefly mention ring networks. Ring networks are great. Lovely circulant structure. Basically, it means I know all the eigenmodes of the ring in closed form. So let me choose a connectivity. It just depends upon distance. So you interact over distances. Delays are also distance dependent. You've got an intra delay, so node to self. There's a thing called Tor intra, and all the other delays are just multiples of Tor inter. And you can use this theory, this framework, to track out things like the synchronous solution in a network or a traveling wave in a network. Okay, so you can begin to build a bifurcation theory, not for nodes, but for networks. And here I'm just varying the internode delay. Okay, and also you see dashes and solids. I can do stability theory. Okay, so those of us that like using numerical bifurcation packages, you can't just chuck this problem in one of those. You have to create your own bespoke approach, and this is the start of a bespoke approach. But then you can go back to modes. We can say, well, I've got a network. It's Wilson-Cowan. It's got some synchrony. I've got a stability theory. I can start to predict the modes that the system will go unstable to. So there's a characteristic function here now indexed by mode. This is the mode of the ring. So I know the eigenvectors that I'm looking to excite. There's a nasty problem maybe sitting here, but then I can say, well, I can work out when I'm going to excite some sort of wave, traveling wave or modulated traveling wave. Or if you carefully look at indices on these things, they're not ordered 1 to n. They jump around. So you can start to begin to describe all the waves of excitation you will excite in a ring, okay? Not in your favorite connectome, unfortunately. Okay. Because that's where the challenge is. So I figured I would mention some challenges. It's good. How do I keep going with this challenge of studying networks and delays? Well, I mentioned phase reduction earlier. You boil everything down to, I'm only going to study things that oscillate and only study things that interact via, oscillations and their phase differences, but I can respect delays. So maybe that's a sensible thing to do, because in that approach, I can, if you like, I can do lots of linear stability of relative equilibria, and I don't have to make assumptions about living on a ring. I can do, connectome data. It's not really an issue. We live in a world where we have to recognize brains are not just neurons. Some rich years here. Glia, super important. So axons are, insulated by white matter. I'm very interested in this challenge that, Jeremy is leading the charge on. It's hard enough developing a theory, an arbitrary connectome with arbitrary delays, but we shouldn't forget that those delays are also plastic on a much longer timescale than maybe the neuronal activity. But we should think about, as a community, thinking about writing down equations for the speed of conduction, because, time is distance over speed, and then thinking about what classes of white matter speed rules, are consistent with biology and that we can do analysis on. So we know, it's obviously very metabolically costly to wrap myelin around axons. So if we see a lot of metabolic activity, we should probably think the speed along the axon is going to go up, put lots of myelin on. So we can start to think about rules that depend upon activity in the network. And maybe the fact that if I've got a very long fiber, it takes a signal a long time to propagate along that fiber, then I might want to speed up that process for some reason or another. Okay. So we've started to look at these sorts of rules for adjusting speeds, not in arbitrary networks, but in the phase-reduced networks. So here I just showed a simulation of what a ring network could do with distance-dependent delays. You get some lovely clustering. But when you start to add in plasticity, you can get nice behavior. So the nice thing about working with phase oscillator models is that it's very easy to study classes of solution, which we call relative equilibria, even in the presence of delays. So this is what I mean by relative equilibria. I pick a phase at node I, and it just rotates with emergent frequency omega. And I substitute that back in the equations of motion and argue self-consistently for this emergent frequency. Now I can plot that emergent frequency as a function of a parameter in the model, here the natural speed along a fiber. And typically, and it's very common in delayed systems, is that you get lots of multi-stability. So I pick a parameter and I get 1, 2, 3 solutions. Okay, 3 different emergent frequencies pop out in this system just because of the delays. Then I turn on an A plasticity rule, and this is just 1 with this parameter kappa. I make a choice in the model. Okay, so this, whoops, sorry. I make a choice in the model. So I'm saying there's a model of speeds that adjust to their natural speed, and there's some coupling strength kappa within a rule that adjusts the speeds according to their phase differences, lagged by the delay. You know, it's a made-up rule. But what this plasticity rule is just flatten out that solution structure. So you used to have a network with lots of different frequencies, and now whatever parameter you pick, you know, this plasticity rule says, well, you can only have 1 emergent frequency. So this might be a good thing or a bad thing, and it's promoting synchrony, okay, as well. Okay, so we're interested in delays, we're interested in maths, but we, you know, have lots of really fascinating colleagues at Nottingham that come and knock on our door, and this will be my last slide, but Stephen Jackson is a colleague in psychology, very interested in Tourette's, because he's got a wearable device that helps reduce ticking via stimulation of the median nerve. And Stephen again came to us and said, well, we really like an in silico playground to test ideas about optimizing stimulation protocols about, you know, involving people. And he said, well, this is typical data we have. Again, spectrograms with rebound. But now what Stephen's doing is sending in rhythmic stimulation or arrhythmic stimulation. So we might be locking to some sort of stimulation frequency and the rebound. So what we're doing with Stephen is trying to develop these sort of neural mass models to make them fit for this purpose. Now we have to deal with the sensory world, okay, not an isolated cortex. So we need a model of thalamus. We tried to reproduce some spectrograms that would be in the spirit of Stephen's work, but it failed miserably using the neural mass model that I talked about earlier on, until we started to put in, well, we changed the model to include, you know, processing of the sensory information through a model of the thalamus. And the model of the thalamus we chose was, well, or developed, was one that just respected the interesting behavior that the thalamocortical and relay cells had, because they're endowed with intrinsic currents that allowed rebound spiking. So these are currents due to slow T-type calcium channels or HCN channels. So, okay, so we have a route to mean field here. We don't have a route to mean field here, but we have a route, because these currents are very slow, we have a route to firing rate reductions that we've used to bolt two mean field models together. And this is the challenge we're now working on with Stephen, is to explain this sort of data. So there's no results. I'm just saying this is what we're doing. Very happy to chat afterwards about how much fun we're having with this thalamocortical model. And of course, if we have a good thalamocortical model, we can use it for all sorts of other things as well. Okay, so these are the people I work with, mainly at Nottingham, except Hill, who's an applied mathematician, numerical analyst in Netherlands, at Twente, and Anya Byrne, who was a PhD student with us at Nottingham and now is an associate professor in Dublin. And John was kind enough to mention a book. Well, I didn't write that book on neural fields. You know, I just persuaded other people to write chapters. But we've bitten the bullet and we've written our own book now. Okay, so if your library has a space, maybe I should talk to the fields people. They've probably got an excellent maths library. Maybe they'd be up for a discounted version of my book. Okay, so it's not mine, it's mine and Carl Witchford. So I'll stop there.